Okay, for this video we're going to talk about capillary exchange and how that works within the capillaries. Here we've got the arterial side, here we've got the venual side. We're going to talk about all the different pressures in here helping us end up push fluid out and oxygen out, and then push fluid in. We're going to talk about what happens with inflammation, otherwise also known as edema. We're going to talk about baroreceptors, and we're going to talk about what happens if your blood pressure drops and kind of like the things that your body does to help regulate that. So first we're going to start with our capillary exchange. So you have some kind of average pressure going through all of your arteries. We'll draw a little chart here. So you've got your aorta, and then you've got large arteries, and then arterioles, and then capillaries, and then veins, large veins, and then vena cava. And so we're going to start some high pressure up here. I'm going to say it's like, around 120-ish. I'm going to, and then right here, say about 80, maybe not that many waves. This right here, it's about 30. Those are in millimeters of mercury. So this is kind of like the pressure. These things will change as your heart pumps, so systolic and diastolic. But once you get past those large arteries and you're into the arterioles, your pressure stays relatively constant. So you can keep a constant pressure within your capillary, because that helps what controls the capillary exchange. The major thing that helps a lot is, like, say you're working out really, really hard, you're getting blood pumping a lot. You don't want to burst this capillary, because if you put too much pressure in, this is only a single layer of endothelial cells. So if those burst, you get blood all over the place into your interstitial fluid, and we don't want that. That's not good. So around your arterioles, they have, this is going to be not the best drawing ever, but this is what's called the precapillary sphincter. And so it will contract or dilate to help maintain the approximately 30 millimeters of mercury inside the capillary. So what helps the capillary push fluid out? Oh, I didn't draw the lymph. Actually, we'll get there. So there's several pressures that determine fluid leaving. So we're going to talk about several pressures. This 30 millimeters of mercury is pressure inside the capillary pushing out. So it wants to leave. So we have 30 millimeters of pressure pushing out. Here we've got a bunch of proteins. These are impermeable solutes. The majority of these proteins is albumin, the major protein within your blood plasma. And so you have some kind of movement of water wanting to move into the capillary because of that. And so that one, we're going to say it's around 28 millimeters of mercury. And this is called BCOP, or blood colloidal, because colloid, stuff in solution, osmotic pressure, water wanting to move in. And this one is called hydrostatic pressure. Your HB, that's the pressure inside the capillary wanting to push out. The next one that we want to deal with is we have these proteins outside. You have cells in your interstitial space. This is some kind of tissue, and cells produce proteins, and cells are largely proteins. So we have some kind of proteins out here in the interstitial space, and we have water in here, wants to move to areas of high concentration. So we have some kind of pressure here, and this is around like 8 millimeters of mercury, and we call this ICOP. So this is interstitial colloid osmotic pressure. And then the fun thing that we have is we have lymph vessels. These aren't perfect. You'll lose some fluid out. And so we have lymph vessels, which kind of just suck up things. And it's sucking up fluid at about 3 millimeters of mercury. So that pulls fluid in here, pulls fluid out. So you could even have here some kind of a pressure of around 3 here pulling out to replace that's being lost. So if we were to total up, I'm going to erase this. If we were to total up our pressures moving out of the capillary, we've got 30 here, 8 here, and 3 there. So that ends up adding to about 41 wanting to go out. And we have 28 wanting to move in.
Hey, Jacob.
Hey, Caden. I'm currently teaching. Do you want to stay in here for my video?
Sure. Actually, there is I don't know if you checked the room schedule.
Is there another thing that's happening?
There is a thing that's happening.
What time?
In about 5 minutes.
Oh my gosh. Okay, sorry about that. I had to move to a different room. It's not amazing. Hang on, let me see if I can go change those lights. So hopefully you can see maybe at least a little better. No, it's gonna be fine. Okay, so we'll pick up where I left off. So we've got pressures moving out. So we've got a total of 30, 8, and then 3 pulling from here. So that's a total of our 41. 41 pulling out of the arterial side, and then we have 28 pushing in. And so that ends up being a total of 13 out if you were to add these two pressures together. On the venule side, so our B cup is the same, I cup is the same, and then our IFP is the same. IFP stands for interstitial fluid pressure. The thing that changes is our hydrostatic pressure. On the venule side, because the capillary has some length, the friction of the fluid with the endothelial cells slows them down and decreases the pressure. So the pressure out here is only around 10 millimeters of mercury. And so we've still got B cop, we've still got I cop, and we've still got IFP. But now if we add this up, we have 10, 3, and 8. So we have 21 going out, and then we still have that 28 moving in. So in total, we actually end up having 7 millimeters of mercury pressure moving fluid into the capillary. So hopefully you can appreciate that we've got fluid moving out on the arterial side and then fluid moving in on the venule side. So that's our capillary exchange. When it comes to edema or any kind of inflammation, so what happens is, say you get like a cut. We're gonna put a great big hole right there. What happens is these proteins, which are normally impermeable to the membrane, are able to leave. So they'll just leave and they'll kind of just go all over the place. What happens is that drops our B cup. So our B cup goes down. Maybe it drops to like 20, maybe even 15. What that does is that will increase how much is leaving. So much so that this is going to decrease. We'll drop this down to 15 as well. We actually end up getting a net movement out on both sides. And so you start getting a huge buildup of fluid outside in the interstitial space. And that's what the inflammation and edema is. This largely happens, you get histamines that get released and start creating holes in the capillary to let fluid rush in. And then in the next video, I'm going to talk about how that's taken care of with platelets and blood coagulation and all that. So that's capillary exchange. The next thing that we're going to talk about is baroreceptors. So I'm going to erase this. Draw a crudely drawn heart. Great. Here's our aorta. Goes out, whoop-de-doo. And then you've got 3 branches. So, and then we're going to draw, so the brachiocephalic, that's what this one is. That's your brachiocephalic artery. You have branches coming off of that underneath your head, and these are called your carotid arteries. Left common carotid will break off into those. So around these, we've got on them, actually I'm going to draw them a little bigger. And then on the aorta, so these little black things are called baroreceptors. And so what the baroreceptors do, how well can you see that? You can see it well enough. Okay, so your baroreceptors are stretch receptors. And so they help sense the blood pressure within the aorta and within the blood. So if they're getting stretched, because you're pumping a lot of blood, high blood pressure, they're going to get stretched more. And so they're going to be sending signals to the brain that says, hey, we're getting stretched, we have high blood pressure. And that will be the same thing in your carotid arteries. If you have lower blood pressure, they won't be stretched as much, and so they'll be sending signals, they'll stop sending signals to the brain, and the brain will interpret that as, oh, we have low blood pressure. And so that can largely be controlled through sympathetic and parasympathetic innervation of your receptors on the heart to increase heart rate, which will increase your blood pressure, or to decrease heart rate, which will decrease your blood pressure. Or you could potentially control contraction of arterioles and mess with peripheral resistance. Our equation, so mean arterial pressure or blood pressure is equal to our cardiac output times peripheral resistance. Cardiac output is heart rate times stroke volume. So if this decreases and we want to keep it within our range, we can increase the cardiac output, which is increasing either stroke volume or increasing heart rate, or we can increase peripheral resistance, and we can do that by either decreasing that's mainly just controlled by vasoconstriction or vasodilation. Cool. So what's the next thing? Baroreceptors we talked about. What happens if we have a very, very quick low blood pressure? So say we're pumping the heart and then you get some kind of occlusion somewhere down in the bloodstream. And so you start getting less blood to this side, and start getting less blood here, you're pumping less blood here. So overall, for some reason, you have less blood. Maybe you have a serious injury, you start losing a lot of blood pressure goes way down. So there are a couple ways that you can deal with that. The first thing that will happen is a really interesting thing. So here we've got some kind of blood vessel, and say you get some kind of massive gash in here. The first immediate reaction that is going to happen is, this is the smooth muscle around it. What's going to happen is it's going to constrict. So as that tightens down, you have immediately less blood flow leaving, and you get less blood flow here. And so that's preventing further decreases in blood pressure because this is tightened. However, this doesn't last forever, and so our body has to have some other ways to help deal with this. Depending on what's happening, we can go through, let's see, we've got active and reactive hyperemia. There's vasoconstriction, or, what was the other one? Hang on, give me a second while I try to remember this one. Oh, and sympathetic regulation. Yeah. So our sympathetic regulation, this is kind of your intrinsic vasoconstriction that will happen on its own. You can get continued constriction of this through innervation from the sympathetic nervous system. If you remember, your smooth muscle has A1 receptors, not A1, alpha 1 receptors that come from the sympathetic nervous system. Those can cause your blood vessels to contract. The smooth muscle in them to contract. The other thing that will help is release of paracrines. And so, yeah, paracrines. So we've got two different kinds of things. So we've got active and, gosh dang it, I'm left-handed. We have to get in the way. So active or reactive hyperemia. And so what this means, hyperemia means you just have increased blood flow. So this will happen to counteract decreased blood pressure. If you want to increase blood pressure, you can increase blood flow, increase how much blood is going through. So we're going to get rid of this. Active hyperemia happens if you are exercising or you're doing something that requires a lot of metabolizing within skeletal muscles and cells. And so as those work, they're releasing CO2 and using up O2. And so as that happens, you want to increase the amount of O2 that's going through there. And so as heart rate increases, you start pumping more blood through faster, and you will, because you're increasing blood flow, you're going to move in more oxygen into the area that needs it and pump out more of that CO2. And so that's your active hyperemia. Your reactive hyperemia is, say, you've got some kind of constriction or occlusion within the blood vessel that suddenly goes away. And so you have this huge increase in blood flow. And so the way that this is largely controlled is, so our blood vessels, this is a terrible marker. We're going to use this one instead. That's not any better. Okay, maybe the black one. Okay, so here's our blood vessel. Each of these lines. So each of these blocks represents one of your endothelial cells. So your endothelial cells will release paracrines. You have nitric oxide, or NO, or ADP. And so in times of low blood pressure after an occlusion, they will release these two things, which are potent vasodilators. And so they will increase the radius and they will allow the blood flow to increase. And so that's your reactive hyperemia. And I think that's it. Let me double check. Okay, there was one other thing, and that's myogenic regulation. So this helps control. So the smooth muscle, we're just going to draw like this. The smooth muscle around your blood vessels, they have stretch receptors, mechanically gated calcium channels. And so when they start to, say you're pumping a bunch of blood through and they start to stretch, as they stretch, those receptors will open and they will let calcium come into the smooth muscle. When calcium comes in, the smooth muscle is going to contract, and you're going to decrease your diameter of the blood vessel to try to maintain your homeostatic pressure. And so that's the myogenic regulation. And so it works a lot better for vasoconstriction. I mean, as you get less, they're pushed less, so they'll open more. So you might get some level of vasodilation, but they're much better for vasoconstriction. And that's everything.